Welcome everyone to the Theoretical Computer Science seminar at Jagiellonian University. Today our speaker is László Végh from London School of Economics. László did his PhD in 2010 in Eötvös University. Then he had a postdoc at Georgia Tech, and then he started work in London School of Economics. He is very famous of his work in exact approximation algorithms for various optimization problems, and perhaps most notably the constant factor approximation algorithm for asymmetric TSP, which is joint work with Ola Svensson and Jakub Tarnawski. And today, László is going to tell us about interior point methods, that they are not much worse than Simplex.
Yeah, thank you very much, Bartosz, for the introduction and for the invitation. I'm sorry I couldn't make it in person, although I really was hoping to. Feel free to interrupt the talk at any point in time if you have some questions. So this is based on joint work with Xavier Alamijon from Paris, Daniel Dadusch from Amsterdam, Georg Loho from Twente, and Bento Natura, my former student at LSE, who is now a postdoc at Georgia Tech. And so, well, you know, it might be a bit of a strange title, so I'll try to, because we, of course, know interior point methods are much better than Simplex, but actually that there is an interesting aspect to it, and I'll first try to highlight this context. So I'll be talking about linear programming algorithms. Let's think of linear programming in this equality form. Actually, can you see my mouse? Yeah, so we have a linear objective we want to minimize over a set of inequality constraints, which are of like greater or equal form. D will always denote the variables and the number of constraints. And another important parameter, if we want to talk about running times, would be the total encoding length of this rational input. So let's assume all these numbers are given encoded as binary represented rational numbers, and L would be the total number of bits describing this matrix, the right-hand side B, and cost function C. And so the first algorithm, which was at the very beginning of the history of linear programming and still a very popular method, is the Simplex by Danzig from 1947. And so this is an algorithm which in practice does very well, and somewhat disappointingly, if we look at the worst case complexity, then it can be exponential. The first such example was given by Klee and Minty in 1970, and of course one can come up with various pivot rules, but typically or for most important ones, exponential examples are known. So then there was this big question of the 70s when looking at it from the computational complexity angle, do we actually have a polynomial time algorithm for linear programming? And polynomial time in the standard Turing model, it would mean that the encoding length of this problem is L, the number of bits needed to describe this input. So can we get an algorithm which runs in poly of L running time? And so there were two very significant developments at the late 80s, late 70s, early 80s, was the ellipsoid method by Kachelyan, and then interior point methods by Karmarkar. And so these are all algorithms that use very different techniques and approaches. And so just a little high level thoughts on why linear programming remains such a fascinating problem to work with to this day is that it's really that there is a fundamental tension between two aspects, because you can see it as a discrete optimization problem and a continuous optimization problem. In discrete perspective, and that's how like Simplex looks at it, you have this high dimensional polyhedron where the vertices correspond to basic solutions, and then you can move on edges. That there is very fascinating polyhedral combinatorics, how you can move between solutions. And as a matter of fact, you can really have compute exact optimal solutions. But then where these polynomial time algorithms came from is from the continuous side. You can see linear programming as a simpler special instantiation of convex programming, where you can look for continuous, in a continuous convex domain, you're looking for solutions. You typically in these algorithms, you are only looking for, or can naturally just get approximately optimal solutions, but then there are very natural like geometric potentials that you cannot really infer them from the combinatoric structure, such as for the ellipsoid method, one can argue about volumes, and that there are very nice analytic ideas in interior point methods. But then, so this is how whether do interior point methods really beat Simplex, or can they? So this is kind of what was the starting question of our investigation. So first of all, like there has been amazing developments in recent years on fast linear programming algorithms. However, these are all fast in terms of if you want to find a epsilon approximate solution, then you can get there very fast for natural notions of approximate solutions. What we now in this talk, we don't make any compromises. You want to get an exact optimal solution. Now, of course, if you have a good enough approximate solution, then you are able to convert that to an exact solution. But as we'll see later, there are sort of heavy dependencies there on the input, which we would like to get rid of. So now Simplex, a good thing about it is really moves between these vertices of the polytopes. If it stops, it does stop with an exact optimal solution. And what we also know is that it is exponential in the worst case. Like this polytope can have like 2 to the n vertices, but that's or n choose the vertices. If it's not doing any cycling, then we after we visited every vertex, surely we did get there. So like Simplex at least always terminates with an exact solution in 2 to the n time. Now, what these ellipsoid and interior point methods, they can also give you the exact solution, but then you have this poly of the bit complexity dependence. And one could imagine linear programs where like this bit complexity can be very huge. I mean, you do need exponential number of entries, but in that case, like this polynomial turtle can catch up with the exponential Achilles. Like so like you could, in theory, this poly L, it doesn't have any bounds in the number of n in terms of n's. And so of course, like this seems like it's kind of an artificial problem setting, but as it turns out, there are like fairly natural classes of problems which you can reduce to linear programs, but you need to use exponential size coefficients. So it does have kind of a theoretical importance, whether we can solve like LPs with arbitrary entries. And so now the starting question for this talk is there just any function f of n and an interior point method where the running time is, on the one hand, it's polynomial in the standard sense, but it's never worse than some function that only depends on n. So there are two more reasons for considering this question. One is really so one will be the quest for strongly polynomial algorithms for linear programming, but just in the context of interior point methods, somehow they're like we are doing very fast progress in terms of optimality gap, but like the question is, could we somehow, if we have very bad entries, bad conditioning, like spend infinite amounts of times seemingly making progress while not getting actually improvement in terms of what's the current best vertex of the polytope we are comparing against. So it's sort of really is kind of an endurance test for interior point methods, whether we can beat this, get a bound which only depends on n. And yeah, so let me have a few words about weakly versus strongly polynomial algorithms. So I already told you, what's the standard Turing notion of polynomial time algorithm for linear programming. This would be polynomial in L, but in this context we call this weakly polynomial algorithms. And we contrast this to strongly polynomial algorithms. So in a strongly polynomial algorithm, we would want to sort of make the running time independent of the encoding size and just make it dependent on the dimension of the problem, how many variables and how many constraints we want to have. And the way it can be formalized, first of all, it's sort of a purist computational model, which just allow elementary arithmetic operations and comparisons. And we want the number of all such operations to be independent of the encoding length. Now, that said, of course, if you have two really big numbers, you need to add them up. That takes a long time. Well, so, but that happens inside, like every addition, subtraction takes a unit time. To make sure we cannot cheat this way, we also require that the algorithm is in p-space, which just means that the bit complexity doesn't do anything nasty, it doesn't explode during the computation. The other way to think about it is you could somehow try to think of computational model with real numbers. Let's say you have an oracle to add up and multiply real numbers. Can we then get a bound like in terms of the dimension for this linear programming algorithm? And just to give you some idea, for example, if you look at Dijkstra's algorithm, whatever horrible numbers there could be, it always runs in number of edges plus number of vertices times log the number of vertices, number of actually just additions and comparisons. So is this notion clear? And yeah, so this is sort of, one very big question of optimization. Is there a strongly polynomial algorithm for linear programming? It's actually on a list by Stephen Smale of like the mathematical problems for this century. It's already 2022, which we still haven't solved it, and I don't think we are very close to solving it. But at least that's a question I really like and have been trying to approach some special cases from different directions over the years. So first question, like this would be actually like the Simplex method has been the candidate in waiting for a very long time. It really has this very nice combinatorial structure. If it stops with an exact solution. So people have been trying to prove that for a very long time, that maybe with some variant it could be strongly polynomial. But then that there is actually already in the 50s, people realized there is a fundamental geometric question behind. What Simplex is doing, it's finding a path in an exponential size graph where the vertices are the vertices of the polytope, edges are the edges of the polytope connecting them. So the baseline for Simplex to be able to be polynomial would be that the diameter is actually bounded. So Hirsch had this very nice conjecture that with n facets in n dimensions, that the diameter would be at most n minus d, which is clearly sort of a tight, the best possible bound one can hope for. And it took surprisingly more than 60 years or more than 50 years until this was refuted by Santos, but refuted by a little bit. So that there is a more robust version, which is the polynomial Hirsch conjecture, which is if we are in d dimensions in n facets, then the diameter would be just polynomial in these. Again, this wouldn't mean that Simplex would be strongly polynomial. It would be just sort of a clear necessary condition, and it's still, you know, this also gets like the holy grail qualification of open problems. It's itself a very tantalizing open problem, that the best bound in terms of like n and d is it has been slightly improved since then, but there is a beautiful paper by Kalai and Kleitman, which is like quasi-polynomial n to the log d type of bound. So Simplex has been waiting to be shown to be strongly polynomial, but again, there are like more fundamental issues there, and of course it's not easy to refute that a certain pivot rule is not efficient, but proving it is even harder, and usually wrong when there have been many attempts. So what, just to give you an overview, is that actually what's sort of if we can't get strongly polynomial in general, for what special cases can we do this? And well, so that most of these special cases come from network optimization problems, like minimum cost network flows was like a big breakthrough by Tardos in the 80s, and then two variable per inequality system, certain Markov decision processes. So there are these nice combinatorial examples. If we want to look for a general linear program, also by Eva Tardos, this is a more general result I'm mentioning here. She gave an algorithm where the running time, so in this LP, we have the constraint matrix A, right-hand side B, and cos C. So can we at least eliminate some of these from the running time? And apparently we can get an algorithm which works with arbitrary B and C. So those running time doesn't depend on them. It only depends on the constraint matrix. And what she showed is that if we have an integer constraint matrix and look at the maximum subdeterminant of this constraint matrix, then there is an algorithm that is polynomial in n and the logarithm of this maximum subdeterminant. So this log of maximum subdeterminant is bounded by L. So this is in particular a polynomial time algorithm, but it's stronger again in the sense that it only depends on the constraint matrix, not B and C, and in just this very particular way. And so this still sort of extends ideas from network flows. It's sort of a black box algorithm of a combinatorial flavor. There has been like a very surprising direction where these results got strengthened. Namely, it turned out that interior point methods, which really come from the very continuous side, they provide, like, in a sense, much more robust and general results than generalizations of the Stardust results. So there is a particular class of interior point methods called layered least squares interior point methods. They were introduced in a fascinating paper by Vavasis and Ye in 1996, and that there has been quite some follow-up work in the 2000s and recently with Daniel Dadouche, Sophie Huiberts, Bento Natura, we revisited and gave some stronger versions. So what these, I'll talk a bit later about this, but just to give you a high-level summary. So here, this is an interior point method that terminates with an exact optimal solution, which is already very rare for interior point methods that normally just get approximate solutions. And the number of iterations is bounded in polynomial of n and the logarithm of a certain condition number of the matrix, which is we call that the circuit imbalance measure. So this, I give you the definition, although it won't be very important for the talk. We look at support minimal vectors in the kernel of this matrix, which are supported by circuits of the associated matrix. We look at the largest possible ratio between the non-zero entries, and the maximum over all circuits and all pairs of entries is the circuit imbalance of this matrix. You have a totally unimodular matrix. This will be one. And in fact, like if you have an integer matrix, then will be upper bounded by the maximum subdeterminant, but it can be much better. And in fact, it's always defined. So this is something that actually works in the real model of computation. You don't need to make any integrality assumptions. It's like a geometric measure. And like in terms of the general LP, well, that there is one improvement I'll talk about later, but this is sort of the type of dependence we can get in this strongly polynomial direction. And okay, so this was perhaps a little long introduction. Now that the rest of the talk will be in three parts. First, I give you comparative upper and lower bounds on simplex and interior point methods, where I talk about our new main result, which is an interior point method that's in a sense approximately optimal in its iteration complexity in a very strong sense. And in the second part, I'll relate this key concept which comes up in the analysis which is the straight line complexity of the central path, and make a relate it to the simplex method. So the simplex will actually help us bound the running time of interior point methods. And then in the third part, I will give you some high level ideas of how the main result is proved and what our algorithm is actually doing. So first part will be this show off between simplex and interior point method. So I mean, I don't assume much or any familiarity with interior point methods. I'll just talk about them in very general terms and show some pictures. So like a very general scheme would be the following. We take some thing called the barrier function, which the most popular one, and that's what we are going to use, is the logarithmic barrier function, which is the negative sum of the logarithms of the slacks. So if you have a feasible solution, then in every inequality, aix minus bi will be positive, and I take the logarithms of these values and the negative of this sum. So what is this barrier function doing? It's trying to push us away from the boundary. Like the closer we get with aix to bi, like the more angry this logarithm is becoming, and so then we are getting really bad terms, really big terms. Now, what this path following paradigm is doing, if we take any like positive value mu, and we instead of so we relax the conditions, constraints into this barrier function, and we look at the minimizer of the objective function plus mu times this barrier function. So what it is telling us, like if we go with mu, again, this barrier function will like make sure we are looking at feasible points, otherwise it would be undefined. And when we start with a very high mu, then the cost doesn't really matter. Then we will be at somehow for this log barrier at the analytic center of the polytope, which is like the in a way the most internal point, keeping away from the constraints as much as possible. And as we start decreasing the temperature and this mu goes down, then we are getting closer and closer, like the objective is becoming more and more important. And yeah, as we go along, in the limit, we will converge to an optimal solution of the original linear program. And so the good thing about this formulation, it's a convex function. We can use general convex optimization techniques to minimize it. And in fact, interior point methods by and large use Newton steps, but in a way that the target is moving, this mu is becoming smaller as we go along. And just to give you one particular example, and this is will be sort of the most relevant for us, is the predictor corrector path following method, where the idea would be the following. So we use this standard logarithmic barrier. We have some starting point, which is like not very far from this central path. And then we have two types of iterates. We have predictor steps, which sort of shoot down along the central path while decreasing this parameter mu, but they lose a bit of accuracy. They go further out from the path. And then comes a corrector step, which steers us back closer to the central path. It doesn't make progress in mu, but it restores centrality. And so we keep alternating between these predictor and corrector steps and get down closer and closer to the optimal solution. In every iteration, we need to solve like linear systems of equations, and the progress is measured by decreasing this parameter mu by a square root n, by a factor 2 in every square root n iterations. And actually, this parameter mu in this case will turn out to be a very good proxy for the optimality gap. So you can think of this algorithm also as a natural primal dual interpretation. We get primal and dual feasible solutions where in every square root n iterations, the optimality gap half. So we really zoom in on these pairs of primal and dual solutions. And so just now let's see some comparison table. So for upper bounds, like for simplex, in general, we can give like the number of vertices, and then there is like actually a sub-exponential 2 to the square root d-ish bound by Kalai and others, which is a specific random facet simplex. So that's a sub-exponential upper bound, but that's sort of the best. And that there is no polynomial bound, even like in terms of this capital L bit encoding length. Whereas for interior point methods, for the reasons I said in square root n, this is here what I write is not the arithmetic complexity, just the number of iterations. In square root n iterations, we halve the optimality gap, and halving it like L times for integer problems will suffice to get an exact optimal solution. And then what these layered least squares algorithms do, they kind of replace this numerical dependence by this single condition number, that the circuit imbalance measure. And then we also have lower bounds, like for, again, there's no universal lower bound for simplex, but for many known pivot rules, there are exponential lower bounds, and there is like a very surprising lower bound also for interior point methods, which I'll talk about in a bit later. And now our question is, in these upper bounds, can we like also get a bound which does not depend at all on the matrix or anything? It only would be a function of n, which is also kind of another way to look at it. Can we get some even more fine-grained bounds on upper bounding interior point methods? And yes, so just to sort of get into the mood of how like interior point methods work. So like for this log barrier, we had this x mu, which was the optimal solution at the point for when we add mu times the log barrier to the cost function. And so these points form the central path, and there is a primal dual optimality gap of n times mu between these and the corresponding dual solutions. And what interior point methods do is to decrease this gap by a factor, constant factor at every iteration. But then what I want to demonstrate in a small example, that like this mu, this optimality gap, is not quite the right parametrization of the central path. So if you look at this example, which is like a triangle, but we very slightly tilt the lower edge, then and we want to minimize, like find the lowermost point here, then the central path will like approximately have this red shape. I start from the middle, then there is like a very straight line until I get pretty much into the region of like the second best vertex, and then it takes a sharp turn and goes to the optimal solution. But you see, like this point here corresponds to the mu equals infinity. From infinity to like most of the history, like nothing important is happening. But then if we just look at sort of the multiplicative decrease, then somehow we will spend most of the time on traversing this straight-ish segment of the central path. And so what was sort of a crucial insight in these layered least squares interior point methods, which is like a corollary of what Vavasis and Yev are doing, is giving a sort of a combinatorial structure of the central path. So it cannot like be arbitrary complex. In fact, it has long straight segments. So what they showed, that we can decompose it into n choose 2 parts, which are alternate between like some short and curved segments, but connected by long and straight parts. And what this short, the length in terms of optimality gap or parameter mu, the length of the short segments can be bounded in terms of this circuit parameter, which, by the way, they used a different parameter, but later we figured out that it has this nice combinatorial interpretation. So here we can traverse it by just the standard geometric decrease. And then there can be like arbitrary long straight segments in between. But what these layered least squares methods somehow manage to do is detect these long segments and glide through them in time, which again only depends on the log of this circuit imbalance and n, but doesn't directly depend, well, that doesn't depend on the length of this segment in the parameter space. And so they have like a very nice combinatorial analysis showing that this is just n and choose 2 of these segments. And so what I wanted to mention here is one strengthening of these results, namely that interior point methods have a very natural scale invariance, namely I can multiply each variable by a constant. I can multiply the constraint matrix by a diagonal matrix from the positive diagonal matrix from the right, and it actually doesn't change the structure, like it. Central path is invariant under this transformation. Most interior point methods are invariant under this transformation, but the Vavasistia method or the circuit imbalance measure, they are not invariant. So what we actually was a question there. So instead of the circuit imbalance measure, one could look at the best possible circuit imbalance measure one can get under diagonal rescaling. So can we improve the dependence on kappa to this kappa star, which can be arbitrarily better? And so for this, actually, turns out that there were 2 algorithms. There was an earlier one in 2009 by Lan, Monteiro, and Tsuchiya, which will be important in the context of the algorithm I'm presenting today, which is like a predictor-corrector trust region algorithm. It has, however, a caveat. Computing the update steps is much more complicated, and in fact, it depends on B and C, which means that even though the total number of interior point iterations only depends on this kappa star, the total arithmetic complexity there, like B and C, creep back in. And what we had in this earlier paper was like a scaling invariant version of the original Vavasistia method, which gets like a kappa star dependence. And this kappa star also comes up naturally in like some curvature analysis of the central path. So, you know, this was until recently sort of really the state of the art. We can look at like the best we can get is polynomial in n and the logarithm of kappa star, but unfortunately this kappa star, even though it's optimized, it can still be unbounded. And so then the question is, okay, so is this maybe sort of a tight bound, or maybe we can get even better, maybe we could even get a strongly polynomial interior point method. And for those who listened carefully at my comparison table, I already gave a negative answer to that, and let me talk about that a bit. So first, if we want to sort of lower bound how many iterations like any interior point method does, then we can get like a very natural lower bound on this. Namely, let's say I want an interior point method which stays in a certain neighborhood of the central path. And if I look at what this interior point method is doing, it's like moving in straight line segments inside this neighborhood, like all steps move on a straight line inside. So what I can ask for is, like, between any 2 points on the central path, what is the smallest number of segments of any piecewise linear curve that stays inside the neighborhood. Like, for example, here, even though there is some wiggling in the central path between these 2 points, I could just jump there with 1 step. So that's what we can say. Maybe that there could be an interior point method which gets here in just 1 single step. But well, that's if it's like more curvy, then we can give a non-trivial lower bounds on how many steps the interior point method might need. And so one can then like take some neighborhood of the central path and look at the straight line complexity, which is like the minimum number of segments to go from any starting point to the endpoint, the optimal solution. One could, of course, look at different neighborhoods. I won't want to go too much into that. There is like a wide neighborhood, which is sort of the biggest that can come up in algorithms typically is when I look at points whose such that on every constraint, the slack on that constraint is within a constant factor of the slack of the corresponding central path point. And what they showed in actually a beautiful paper using tropical geometry that is an explicit simple family of parametrized linear programs, which I even put up in here on the slide. So t is here a parameter. For each value of t, we get a linear program. And what they show is that however wide neighborhood I take, if I pick t large enough, then the straight line complexity of this neighborhood will be exponentially large. Like, what this means is that for this parameterized family, for a large enough parameter value, whatever big tolerance my interior point method would allow in terms of neighborhood, it necessarily needs to take an exponentially many steps. And the consequence is that there is no path following method staying in the wide neighborhood of the log barrier central path that can be strongly polynomial because of this reason, this exponential lower bound. And in fact, more recently, they extended it. They have an even stronger result, which now works for any self-concordant barrier function. Like, it completely knocks out all hope that interior point methods could be strongly polynomial. And then the proof is via whoever of you are familiar with tropical geometry, one can look at sort of a log limit of this family of linear programs, which will end up in this funny right angle bounded tropical linear program where the central path becomes like a piecewise linear zigzag curve, and there they can basically argue that in the one can read off this argument from the tropical limit. Okay, so this is the lower bound, and then finally I'm ready to state our upper bound, which is in a sense a matching upper bound, not tight, but conceptually quite there. So what it says is that if I take any starting point in the standard L2 neighborhood, that there is an interior point method that stays inside this neighborhood and returns an optimal solution in the number of iterations that is bounded by n to the 1.5 times the logarithmic terms times the straight line complexity of any wide neighborhood. So what basically we are looking at, we look at, so our interior point method stays in this small neighborhood, but I can look around in any arbitrary wide neighborhood. If I find there a piecewise linear segment path that goes from this area to the optimal solution in like 4 steps, then our algorithm will have this 4 times, well, like a polynomial overhead, which like will depend logarithmically on how widely I open up this neighborhood, but otherwise it matches this bound, which again is sort of a lower bound for any interior point method working in that neighborhood. So in other words, our algorithm is not worse than by a factor n to the 1.5 times whatever any interior point method may do, and we can in fact get it for even more general like it can be really against any barrier function. And what of course, you know, if you would give me this this piecewise linear curve here, that would of course make life very easy to sort of design an interior point method which somehow copies what the other one is doing. But the trick here is that we don't have access to the solution of this straight line complexity. So this is just an existential result, like whatever might be the minimum there, we are going to match that. So maybe if there are some questions up to this point, it's a good time to stop a bit.
So maybe I wanted to ask already some time before, this circuit imbalance, was it something developed here for the purposes of analyzing complexity of these methods for solving the integer programming, or it was known before?
Yes and no. So what Vavasis and worked with was a different condition number, this chi bar that was on one of my slides, which is like some norm of certain oblique projections. So what with my co-authors, when we started working on this, the really key idea was to figure out that it actually is like within small factors the same as the circuit imbalance measure. But then so the circuit imbalance, it was actually implicitly used in various contexts over the decades. It also has some integer counterparts which come up in integer programming, like it's very closely related to these different variants to proximity theorems, both for linear and integer programming. So I mean, it's so it's been around, but like the specific connection to interior point methods, it's relatively recent. We have a survey paper on all these circuit imbalances in linear and integer programming on my website if someone is interested in that part.
Okay, thanks.
Okay, but so actually, as in this result, it doesn't directly feature this circuit imbalance. So what actually, just one more side on this result, that for this like straight line complexity, any sort of reasonable interior point method gives an upper bound such that this kappa star in particular gives an upper bound. But then what our second result will be is that we can also get a combinatorial bound on this. We can also bound this straight line complexity by like n choose d for like basically the number of vertices of the polytope. And so that's what I'm going to talk about in the second part. So how can we like forgetting all interior point methods, everything, how can we bound this parameter straight line complexity of the central path? And so what takes us here will our good old friend Simplex will give the answers actually. So what we define first is called what we call the max central path, which will be sort of a combinatorial cousin of the central path. So what does it mean? So let's V star be the optimal solution of our linear program. Like here is the linear program, we have this polytope, and this is the objective direction. So the optimal solution would be, or I guess this point. So now what we want to look at, okay, so let's say we are looking at all possible solutions where we allow violation of optimality by an additive G, so which have objective function at most V star plus G. So that would be actually this. Am I pointing at the right region, or this region? And then for every index I look at the largest possible slack on this inequality among such solutions. So in particular, if I look at this sorry, I was in fact looking at the wrong point. So this is the optimal solution. This is now our region, which is optimum up to G, and the biggest slack on this inequality will be up at this point, right? Like this is basically the point that is the furthest away if we want to maximize this objective against this cut down polytope. So for every index, we can define every constraint, we can define this. And we can think of, okay, how does this SGMI evolve as I goes as G goes from 0 to infinity. So once it went to infinity, we will include all possible feasible solutions. So it will be actually the point that has the largest slack on this inequality, which is up here. But as you start closing in on G, we get a piecewise linear segment, and this would actually correspond to the sets of optimal solutions where we look at the cost function, which is a convex combination of the original cost C and the direction of this this constraint AI. And what this corresponds to, it's you can imagine it as projecting down your feasible region to the two-dimensional plane defined by the objective function and this constraint, and look at the shadow of this. And then on this shadow, I would move from the starting point to the end point. So this is really a nice two-dimensional geometric object. And in fact, this is exactly what a very popular variant of Simplex, the shadow Simplex algorithm, is doing. This is the prominent version where polynomial bounds were given on average case analysis and smooth complexity by Borgward in 1987 and by Spielman and Tang in 2004. And so again, this shadow Simplex path sort of define our for each index I these SGMI curves, which correspond to a piecewise linear non-decreasing concave function, and then each piece corresponds to a basis. So it will be at most the number of pieces will be at most the number of vertices, and then what we define is the max central path, which is simply for each parameter g, we concatenate, we put together all these values sg m of I. So sgm will be this vector which defines the maximum central path. And then for this maximum central path, I define a neighborhood which will be contain those vectors where the slack is within a constant factor of the max central path value. So that the way you can think of it, here we want to, like for a certain optimality gap, we want to simultaneously push every slack as high as it can be pushed with respect for this level of optimality. And what turns out is that if we look at pretty much any self-concordant barrier function, you don't need to know what this self-concordance property means. This is what is sort of the most general property that works with interior point methods, but that will be like that will define a central path which stays in this neighborhood of the central path. So somehow this gives us like a universal neighborhood. You can interpret it as this is where whatever interior point you could come up with, it will live in the neighborhood of this max central path. Now, the way we obtain this max central path is that we individually optimize for each separate coordinate, but so it's actually doesn't give us a feasible solution, but you can get like corresponding feasible solutions by taking n such solutions and averaging them. And now what sort of, so this is actually the nice, pleasant part of the paper, is that from this max central path, we can give a combinatorial bound on the straight line complexity of the wide neighborhood of the original central path, because what basically turns out that the solution we construct from the max central path, again, it will be a piecewise linear curve, because for every individual index, we have a piecewise linear curve where the number of segments is bounded in terms of the number of vertices of the polytope, and then we averaging such curves with still, well, up to a factor n, we will still give a piecewise linear curve. And then what we already get from here is that the straight line complexity of this wide neighborhood has this combinatorial upper bound. And so again, the relevance of this is that if you look at our general statement, it always does like some n to the 1.5 times the straight line complexity number of iterations our algorithm. And now we show that the straight line complexity is at most this n choose v, which altogether then gives us the desired type of bound that it's always just single exponential. So it's sort of matching in a certain sense the lower bound from the tropical construction. And one more thing, yeah, it's like if you were given, so what sort of this is telling us that if in the strongly polynomial sense, whatever you want to know about how good an interior point method can be, you can actually forget like what the central path is or what self-concordance is. Like you don't need to know any analysis, even if you are just a very combinatorially minded person. You can actually just have to basically analyze two-dimensional pictures. You just need to sort of try to analyze that if I look at even just for one coordinate, I have a piecewise linear curve, which is defined by this shadow simplex path. I relax it by a factor 1 minus theta. And what's the minimum number of linear segments I can squeeze in between these two neighborhoods? And in fact, this can always be done greedily. If we start from the infinite direction, you always just have to shoot as far as you can. That's basically the best you can do. Of course, this is not something you can efficiently do, because the number of segments here can be exponentially long. But as a just to give a conceptual bound, this is kind of a new tool we provide for analyzing interior point methods. And then, so I'll definitely go beyond an hour, but hopefully by not too much. I'll in the last part of the talk, we'll give you some idea of how our interior point method actually works. But before that, if there are some questions on this straight line complexity, then we can stop here for a second. All right, so I mean, again, I don't expect people to know how interior point methods too much about them. I just want to give some very high level ideas. So what happens here is that, let's say we know that in a wide neighborhood of the central path, there is a long straight line segment. Now we don't see it, but what we prove that this imposes a certain structure on the corresponding part of the central path. And this is again like a very elementary argument. What happens here? So we basically show a certain polarization property, namely that there are the variables you can partition into two types on this line, corresponding segment of the central path, B and N. And what happens is that in B, as you go down on this line segment, the values of X barely move. They really, or the slack values of the corresponding constraints barely move. They remain within a constant factor, and they can actually never go up too high as a property of the central path. And whereas on N, the exact opposite is happening, that all the slacks are going down linearly, we are uniformly getting tighter and tighter on the corresponding constraints. Normally, these path following methods come in a primal dual setting, and then I'm only talking about the primal side, but there is also a dual side where the same happens. So what basically happens, this is how we sort of exploit the existence of this piecewise linear curve in the neighborhood, that it imposes this polarization property. Now, of course, how do we know what's this polarization partition? It turns out that that's something fairly easy to detect. What our goal is in this new algorithm, which is a new variant of this layered least squares interior point method, we call the subspace layered least squares method, is that we can traverse any polarized segment in n to the 1.5 log n iterations, and this can be an arbitrary long polarized segment, and we don't have any kappa dependence or anything. It's really this strongly polynomial bound. And for this, we first guess this partition, which basically we just look at what the standard affine scaling step in interior point methods would do, and whichever variables, slack variables it would want to won't decrease by too much. They will be in B, the rest will be in N. And what one can show is that if we are still, it's a very long polarized segment, then if we compute this standard direction at the beginning, it will tell us this partition. So that's actually already a very good starting point. And in hindsight, this is what sort of the Lan-Monteiro-Tsuchiya algorithm was doing, although it was also a kappa star algorithm. They didn't look at straight line complexity or ask these questions, but what we in hindsight realized that they detect this same partition, and what they do with a trust region step is to explicitly try to compute the direction which makes the most progress on decreasing the variables in N while barely moving the variables in B. Again, the problem that this step we don't know how to compute in strongly polynomial time. The running time dependence will be on B and C. And so what our algorithm is doing in this context is sort of a proxy to this. It can be arbitrarily worse than this trust region step in any given iteration, but on the long run, it actually catches up. So what we are trying to do is that we restrict our movement direction along the central path to a certain subspace of possible movements. And the way we choose this subspace would be that basically we have these variables n, which we want to push down very aggressively. And the subspace somehow guarantees us that whatever, even if we push these down by a lot, we can extend it to a full movement direction in B in a way that the movements there would remain bounded. And so I won't go into details here, but this subspace we can get from an approximate singular value decomposition. There's also a corresponding dual subspace. And what is sort of the key of the analysis here is that in like square root n log n iterations, in every square root n log n iterations, we either get to the end of this polarized segment, or one of these subspaces we are working with will become one dimension larger. And that can happen at most n times or 2n times. So that's why we get this order n to the 1.5 log n iterations to traverse this segment. And that's pretty much what I wanted to say about the algorithm. Again, it's some technical details in there, but just to state again, like the high level result here is we can indeed get the, at least if we don't care about factors of n, which of course in practice we should, but if we are into the strongly polynomial game, then just conceptually we get the best of both worlds, the better of the best strongly polynomial bound and a single exponential. In fact, even stronger, we get that this is sort of a universal interior point method in the sense that it's doing just a little worse than any possible interior point method to find the exact solution. And then we also show that the same property holds for this trust region algorithm. And so, yeah, just a few concluding remarks is that actually in the title I backtracked saying that interior point methods are not much worse than Simplex. There's still a gap because Simplex has sub-exponential variance, whereas interior point methods do have this exponential lower bound. However, that's exponential as in 2 to the d, the dimension, whereas our upper bound is 2 to the n. So there is actually a possible improvement in there. And then, yes, so some questions is, what can we say, like for more general convex programs, like semi-definite programs, can we get in a similar sense near optimal path following methods? Can we maybe say something if there are like some nonlinear segments in the IP? Can we improve this factor? It certainly shouldn't be tight. It's a very generous analysis. And one thing I am particularly interested is that now we sort of have a big new hammer on like, can we find new classes of linear programs where we can get new strongly polynomial algorithms? One outstanding question here is like the minimum cost generalized flow problem, where we don't have strongly polynomial algorithms, and we don't know if this or any interior point method, meaning that this particular is strongly polynomial or not. And yeah, this was it. So thank you very much for your attention. And if you have any questions, please ask.
Thank you very much, László.